It begins with a mirror, not a glass mirror like the ones we hang in hallways to check our reflections, but a mosaic of 18 hexagonal segments coated in a microscopic layer of gold, suspended in the absolute cold of deep space. It floats 1 million miles from the nearest human being, at a gravitational balance point called L2, turning its back on the sun, the earth, and the moon to stare into the eternal dark. The machine is the James Webb Space Telescope. When it launched, the scientific community held its collective breath, not just because of the engineering risks, but because of the specific question it was built to answer. For decades, we believed we had a working timeline of the universe. We thought we understood the sequence of events that turned the chaotic energy of the Big Bang into the structured, star-filled cosmos we live in today. The story went like this. The universe began in fire. It expanded and cooled. Then came the Dark Ages, a long era of suffocating fog, where hydrogen gas filled the void. Slowly, patiently, gravity began to pull that gas together. The first stars ignited, lonely, fragile sparks in the dark. Then, over hundreds of millions of years, those sparks gathered into small, messy clumps. Eventually, those clumps merged to become the first primitive galaxies. It was a sensible story. It fit the math. It fit our simulations. It suggested that the early universe was a place of scarcity, where structure had to be earned through the slow, grinding work of gravity over eons. Then Webb opened its eyes, and the story collapsed. The telescope didn't just look at the universe, it looked backward through it. Because light travels at a finite speed, about 300,000 kilometers per second, distance is effectively a time machine. The farther away an object is, the longer its light has taken to reach us. When Webb focused on a patch of sky that looked empty to our eyes, it was collecting photons that had been traveling for more than 13 billion years. It was taking a snapshot of the universe as it existed in its infancy. We expected to see toddlers. We expected to find faint, irregular blobs of light, galaxies that were just beginning to figure out how to be galaxies. We expected to see the cosmic equivalent of a construction site where the foundations were barely being poured. Instead, we found skyscrapers. In the very first deep field images, hiding in the infrared darkness, were galaxies that had no business existing. They were massive. They were bright. They were fully formed. Some of them contained hundreds of millions, even billions of solar masses worth of stars. And they were sitting there in an era just 300 to 500 million years after the Big Bang, where our models said the universe should have been nearly empty. It was a shock that rippled through the entire astronomical community. These objects were so impossibly large for their age that researchers briefly gave them a nickname that sounds less like science and more like a warning: universe breakers. To understand why this terrified the theorists, you have to understand the sheer stubbornness of gravity. Gravity is the architect of the universe, but it is not a fast worker. It is weak. It takes time to overcome the expansion of space. It takes time to pull diffuse gas into a cloud dense enough to ignite fusion. In the standard model of cosmology, you cannot simply snap your fingers and create a galaxy. You have to build it, brick by brick, merger by merger. Standard physics dictates a speed limit on this construction, Gas has to cool down before it can collapse. Dark matter halos have to grow large enough to trap that gas. If you see a galaxy with the mass of the Milky Way, it implies a certain history, a long chain of events that leads up to it. Finding these massive galaxies less than 500 million years after the Big Bang is like walking into a nursery and finding a teenager with a full beard and a doctorate. It doesn't just look wrong. It implies that the biological clock we are using to measure age is fundamentally broken. The discrepancy wasn't small. When astronomers ran the numbers, comparing the amount of light these galaxies were emitting to what our best simulations predicted, they didn't miss by a few percent. They missed by factors of 10, sometimes even more. This phenomenon quickly earned a name: the too much light, too early problem. The first reaction, as it often is in science, was denial, not in a malicious sense, but in a rigorous one. When a machine tells you something that violates the laws of physics as you understand them, you don't rewrite the laws, you check the machine. Was the telescope calibrated correctly? Was it possible that we were misinterpreting the data? Astronomers scrambled to find alternative explanations. Maybe these galaxies weren't actually that massive. Maybe they were just incredibly bright for some other reason. Perhaps they were closer to us than they appeared, masquerading as ancient giants. Or maybe the dust in the early universe behaved differently. Tricking the sensors, they checked the redshift. That, in astronomy, redshift is the most reliable yardstick we have. As the universe expands, it stretches the light traveling through it, shifting it toward the red end of the spectrum. The more the light has stretched, the longer it has been traveling, and the farther back in time it comes from. Webb is designed specifically to read this infrared signature. The measurements held. These galaxies were indeed sitting near the dawn of time. Then they checked the mass. Maybe these weren't giants. Maybe they were just small galaxies undergoing a frantic, temporary burst of star formation that made them look big. A small flashlight can appear as bright as a distant searchlight if you catch it at the right moment. But then came the spectra, the chemical fingerprints of the light, and this is where the mystery deepened from a puzzle into something genuinely unsettling. Stars are the factories of the universe. The Big Bang produced almost nothing but hydrogen and helium. Every other element, the carbon in your cells, the oxygen in your lungs, the nitrogen in the air, was forged inside the crushing heat of a stellar core. When a star dies, it explodes, scattering those heavy elements into the cosmos to be incorporated into the next generation of stars. This takes time, a lot of time. If these early galaxies were truly the first generation, they should have been chemically simple. They should have been made of pristine, primordial gas. But when Webb analyzed their light, it found traces of carbon, oxygen, and nitrogen. Think about what that implies. It means we weren't looking at the first stars. We were looking at the children, or perhaps the grandchildren, of the first stars. It means that in the B of an eye, cosmically speaking, an entire generation of stars had already been born, lived their lives, burned through their fuel, and died in supernovae to enrich the surrounding gas. The timeline wasn't just tight, it was impossible. To get that much chemical complexity that quickly, the universe would have had to hit the ground running, forming stars at a rate that defies our understanding of how gas collapses. This is the universe breaker problem. It suggests that the early cosmos was not a dark, quiet place that slowly woke up. It was a place of violent, rapid, and explosive creation. It was crowded, it was busy, and it was doing things that, according to our textbooks, it shouldn't have been allowed to do. The mood in the scientific community shifted from skepticism to a kind of electrified anxiety. We had built a time machine to see the beginning, and we arrived to find the party was already in full swing. As the data continued to pour in, the problem compounded. It wasn't just the galaxies themselves that were too big, it was what lived inside them. At the heart of nearly every massive galaxy in the modern universe, there is a monster, a supermassive black hole. Our own Milky Way orbits one right now. These objects are titans, weighing millions or billions of times the mass of the Sun. We have theories for how these monsters grow. You start with a seed, a regular black hole formed by the death of a massive star, and you feed it. Gas falls in, swirls around, heats up, and gets swallowed. But black holes are messy eaters. As matter rushes inward, it gets incredibly hot and blasts out radiation. That radiation pushes back against the incoming gas, choking off the food supply. This creates a natural speed limit on how fast a black hole can grow, known as the Eddington limit. Based on this limit, growing a supermassive black hole should take billions of years. It is a slow, gluttonous process, yet Webb found them already there, already massive, deep in the early universe. Less than 500 million years after the beginning, Webb detected supermassive black holes sitting in the centers of these impossibly bright galaxies. Some of them were already millions of times the mass of the Sun. This shouldn't happen. If you start with a stellar seed, there simply isn't enough time in 500 million years to grow that big. Even if the black hole was eating as fast as physically possible every single second of its existence. It's like finding a 100-year-old oak tree in a garden that was planted last week. You can water it all you want, you can give it the best fertilizer in the world, but biology has limits, physics has limits, or at least we thought it did. So we are left with a stark choice. Either our measurements are wrong, which seems increasingly unlikely as multiple instruments confirm the same data, or our understanding of the universe's childhood is fundamentally flawed. This is where the human element of science truly shines. There is a specific kind of silence that falls over a room of researchers when they realize the map they are holding does not match the territory they are standing in. It isn't panic, it's a sudden, sharp focus. The realization that the anomalies aren't errors, they are clues. The too much light, too early problem isn't just about counting galaxies, it's about the physics of matter itself. It forces us to ask, how did the universe organize itself so quickly? What was happening in those first few 100 million years that acted as a catalyst, accelerating the growth of structure far beyond what gravity alone should have achieved? To answer that, we have to look beyond the galaxies themselves. We have to look at the invisible scaffolding that holds them up. We have to talk about the dark, because the visible universe, the stars, the gas, the light we capture with our gold-coated mirrors is only the tip of the iceberg. It floats on a sea of something else, something we cannot see, cannot touch, and yet which outweighs everything else in the cosmos, 5 to 1, dark matter. If the galaxies are the skyscrapers of the universe, dark matter is the steel frame hidden inside the concrete. You can't see it from the street. But without it, the building collapses. And if the skyscrapers went up too fast, it's because something about that frame was different than we imagined. We used to think of the early universe as a smooth, uniform fog. But the existence of these universe breakers suggests that the fog was lumpy, it was textured, it was primed for collapse. The implications of this are unsettling. If structure formed that early, it means the conditions of the Big Bang itself might have been different. The initial distribution of matter, the tiny quantum fluctuations that seeded the cosmos, might have been more extreme, or perhaps gravity itself behaved differently when the universe was smaller and denser. We are standing on the edge of a rewrite, not a minor edit, but a fundamental revision of the first chapter of history. The James Webb Space Telescope didn't just show us distant lights. It showed us that the darkness is far more capable of creation than we ever gave it credit for. The question is, no longer did it happen, we know it did. The light has touched the mirrors. The photons have been counted. The question now is, how? How did the universe cheat the clock? How did it forge millions of suns and build gravitational monsters in a window of time that should have been barely enough to cool the hydrogen gas? To find the answer, we have to go back to the seeds. We have to look at the very first objects to condense out of the primordial gloom. We have to consider a possibility that was once considered fringe, a theory that suggests the first black holes didn't start as stars at all. What if they were born big? This is the concept of heavy seeds, clouds of gas so massive and so pristine that they refuse to shatter into stars. Instead, under the weight of their own gravity, they collapsed directly, bypassing the stellar stage entirely, punching a hole in space-time to create a massive black hole instantly. It sounds like science fiction, but as we stare at these impossible galaxies, it is beginning to look like the only way to make the math work. The universe we thought we knew, the one of slow, gradual evolution, is dead in its place, is something wilder, a universe that rushed toward complexity, a universe that didn't wait for permission to build its giants. As we peel back the layers of light, looking deeper into the infrared, we are finding that the dark ages were not dark at all. They were blazing with a light we are only just learning to see. And hiding in that glare are the answers to how we and everything else came to be. The clock is ticking backward. The deeper we look, the younger the universe gets, and yet the more familiar it looks. We are chasing the first moment of structure, the first time gravity won the war against expansion. And what we are finding is that the war was won long before we thought the first battle had even begun. To understand why the universe feels like it cheated, we have to look at the engines driving these galaxies. When we peer into the centers of the massive galaxies found by Webb, those bright, impossible structures sitting just a few 100 million years after the Big Bang, we often find something looking back at us, a single, piercing point of light that outshines the billions of stars around it. These are active galactic nuclei, powered by supermassive black holes, and their existence at this stage of cosmic history is, to put it mildly, a problem. In the modern universe, Supermassive black holes are common. There is one at the center of the Milky Way, a quiet giant called Sagittarius, a star, sleeping roughly 26,000 light years from Earth. It weighs about 4 million times the mass of the Sun. We accept its size because we assume it has had more than 13 billion years to eat, grow, and merge with other black holes. It has had time to get fat. But the black holes Webb is finding in the early universe don't have that luxury. They are appearing when the universe was less than 500 million years old, and yet they are already titans, weighing millions or even billions of solar masses. If you do the math on the back of a napkin, this shouldn't be possible. Black holes grow by consuming matter, gas, dust, shattered stars, but they are not vacuum cleaners that can swallow the universe instantly. There is a physical limit to how fast a black hole can eat. It's called the Eddington limit. Here is how it works. As gas falls toward a black hole, it speeds up and crashes into other gas particles. This friction heats the material to millions of degrees, causing it to glow fiercely. That glow is radiation, light, X-rays, ultraviolet energy blasting outward. But radiation exerts pressure. If a black hole tries to eat too fast, the radiation from its own meal becomes so intense that it pushes the remaining food away. It literally chokes on its own dinner. According to standard physics, a black hole can only grow so fast before this feedback loop kicks in. To get from a small seed to a billion solar mass monster, while respecting the Eddington limit, should take roughly 1 billion years. The universe didn't give these black holes 1 billion years. It gave them a fraction of that time. Yet there they are, fully grown, anchoring galaxies that are chemically mature and blazing with light. This forces us to ask a question that touches on the very origin of structure. Where did the first black holes come from? For decades, the leading theory was light seeds. The idea is straightforward. The first generation of stars, called population 3 stars, were likely massive, formed from pure hydrogen and helium. When these giants died, they collapsed to form black holes, but these resulting black holes would have been small, perhaps 10 to 100 times the mass of the Sun. These are light seeds. If you start with a seed that small, you have to feed it continuously, at the absolute maximum speed allowed by physics, without a single pause, to even come close to the sizes we are seeing. It's a needle threading scenario. It requires everything to go perfectly for hundreds of millions of years, and nature rarely does anything perfectly. So, astronomers have begun to turn toward a darker, more violent alternative, a theory that was once considered exotic but is now looking increasingly necessary to explain the monsters in the dark. What if the first black holes didn't start as stars at all? This is the theory of heavy seeds, or direct collapse black holes. Imagine the early universe. It is smaller than it is today, so matter is packed tighter. It is hotter. The gas is pristine. No carbon, no oxygen to help it cool down effectively. In some rare regions, you might have a colossal cloud of primordial gas, thousands of times more massive than a typical star-forming cloud. Normally, gravity would pull this cloud together, it would fragment, and it would turn into a cluster of stars. But if the conditions are exactly right, if the gas is kept hot enough by radiation from nearby sources so that it cannot fragment, Gravity wins a total victory. The cloud doesn't break apart. It collapses as a single unit. It bypasses the star stage entirely. It implodes under its own crushing weight, punching a hole directly into space-time in a heartbeat. You don't get a 10 solar mass black hole. You get a seed that is already 10,000 or 100,000 times the mass of the sun. You start the race with a head start. If these heavy seeds existed, they would solve the timing problem. A black hole starting at 100,000 solar masses doesn't need to eat at a miraculous pace to become a billion solar mass giant by the time Webb sees it. It just needs to eat normally. But this solution comes with a terrifying implication about the early cosmos. It implies that the dawn of the universe was not a quiet nursery of baby stars. It was a place where gargantuan clouds of gas were silently vanishing into horizons, creating monsters in the dark before there was even enough starlight to see them. This changes how we visualize that era. We used to think of galaxy formation as a bottom-up process, small things merging to make big things. Heavy seeds suggest that in some places, the universe started big right from the jump. However, even a heavy seed needs to eat. And this brings us to the environment these seeds were planted in. The early universe was distinct from the one we inhabit today in ways that are hard to intuitively grasp. Today, galaxies are islands separated by vast oceans of emptiness. Mergers happen, but they are events, rare collisions that take hundreds of millions of years to play out. But redshift is a measure of expansion. When we look back to a redshift of 10 or 12, we are looking at a universe that was physically smaller. The oceans between the islands hadn't stretched out yet. Everything was closer together. This proximity matters. It means that gas wasn't just trickling into galaxies, it was flooding into them. The interactions were constant. In this dense, crowded environment, galaxies collided and merged far more frequently than they do today. When galaxies merge, they don't just gently combine, the collision acts like a funnel. It drives gas toward the center of the newly forming system, compressing it to extreme densities. This is exactly what a hungry black hole needs. It breaks the Eddington limit's usual constraints because the food is being force-fed into the core by the violence of the merger itself. This might explain why Webb sees so much light. It's not just starlight. It's the death screams of gas as it spirals into these gorging black holes. Some astronomers have proposed that what we call universe breakers might not be fully formed galaxies in the traditional sense. They might be smaller galaxies that are incredibly bright because their black holes are eating at a super Eddington rate, briefly outshining their host galaxy by orders of magnitude. If you look at a flashlight beam head-on, it looks blindingly bright, and you might overestimate the size of the bulb. If we are looking down the barrel of a feeding frenzy, we might be misinterpreting the mass. But even after accounting for this, stripping away the light from the black hole to see the stars underneath, the tension remains. The galaxies are still too big. The black holes are still too heavy. The heavy seed theory is gaining traction because it fits the violence of the data. It paints a picture of an early universe that was efficient to the point of ruthlessness. It didn't waste time making small stars that would eventually merge. It collapsed massive clouds directly into darkness. It merged those seeds rapidly in a dense, claustrophobic cosmos. And yet, there is a piece missing from this puzzle. A black hole, No matter how big the seed, needs a structure to hold it. It needs a galaxy around it. And galaxies don't just float in space, they grow on a trellis. To understand how the universe breakers gathered enough material to form skyscrapers in the void, we have to look at the invisible architecture that guides every ounce of gas in the cosmos. We have to look at the web, the visible matter, the gas, the stars, the accretion disks is just the paint on the canvas. The canvas itself is made of dark matter. And if the galaxies form too fast, it suggests that the canvas was woven far more tightly and far earlier than our models predicted. The standard model of cosmology assumes that dark matter halos grew slowly, but the existence of these massive objects suggests that the dark matter scaffolding was already in place, waiting to trap the gas. It suggests that gravity had a head start. We are beginning to suspect that the Dark Ages were organized, that before the first light ever shone, the dark matter had already built the highways and the intersections where the first galaxies would inevitably form. The heavy seeds didn't just appear randomly. They formed at the nodes of this invisible web, the deepest gravitational pockets in the universe. The gas didn't have to wander around looking for a home. It was guided, it was channeled, it flowed along filaments of dark matter like water running down a wire straight into the mouths of the waiting monsters. This changes the narrative from one of impossible luck to one of inevitable physics. The early universe wasn't breaking the rules. It was simply playing a game we hadn't learned the rules to yet. But if the dark matter web was stronger and more developed, it raises a question about the very beginning. What happened in the first moments after the Big Bang to create such deep wrinkles in the fabric of reality? To answer that, we have to go even bigger. We have to zoom out from the individual monsters and look at the collective structure, the architecture of chaos that allowed the universe to build its cities before it had even finished laying the roads. To see the universe as it truly is, you have to strip away the light. If you could turn off every star, erase every glowing nebula, and banish the radiant heat of the Big Bang, you would not be left with empty space. You would be left with a structure so vast and intricate that it resembles the neural network of a giant brain. This is the cosmic web. It is made of dark matter, a substance that does not emit, absorb, or reflect light, yet which exerts a gravitational pull so powerful that it dictates the motion of everything else. The galaxies we see, the universe breakers that Webb has found, are merely the bioluminescent plankton drifting in this invisible sea for a long time. We believed this web formed slowly. The standard model, lambda CDM, suggests that dark matter started as a smooth, almost featureless field. Over billions of years, gravity amplified tiny irregularities, pulling the dark matter into long, thin filaments. These filaments crossed each other, creating nodes, dense intersections where gravity was strongest. It was in these nodes that gas would eventually pool, cool, and ignite into galaxies. It was a graceful, gradual construction project. But the massive galaxy's web is seeing suggest that the foreman on this project was not graceful. He was frantic. The existence of fully formed structures at redshift 10 or 12 implies that the dark matter halos, the invisible baskets that hold galaxies together, were already huge. They had clumped much earlier than we thought possible. This is a terrifying realization for a cosmologist, because dark matter is the foundation. If the foundation was laid that quickly, it means the initial conditions of the universe were far more volatile than our simulations assumed. But a strong foundation alone doesn't explain the speed of construction. You still need materials. You need hydrogen gas to fall into these halos and turn into stars. And this brings us to one of the most significant shifts in our understanding of cosmic plumbing, the theory of cold accretion. In the old view of the universe, galaxy formation was a hot, messy affair. We thought that as gas fell into a dark matter halo, it would slam into the existing gas, creating a massive shock wave. This shock would heat the gas to millions of degrees. Before it could collapse into stars, it had to cool down, a process that takes a long, long time. It was a cosmic traffic jam. The gas was there, but it was stuck in a hot, pressurized sphere, waiting to radiate away its energy so it could finally settle. If this were the only way galaxies grew, the universe breakers would be impossible. They would have starved to death waiting for their dinner to cool. But clearly, they didn't starve. They feasted. Simulations and new data are pointing toward a loophole in the traffic laws. It appears that in the early universe, the dark matter filaments were so dense that they could shield the gas flowing inside them. Instead of crashing into the hot halo and stalling, streams of cold, pristine hydrogen could punch right through the heat, like a needle piercing a balloon. These cold flows delivered fuel directly to the heart of the galaxy, bypassing the cooling process entirely. It was an intravenous drip of pure star stuff. Imagine a construction site where, instead of waiting for trucks to navigate city traffic, you built a high-speed subway tunnel straight to the foundation. You could pour concrete 24 hours a day, non-stop. This mechanism changes everything. It explains how a galaxy could maintain a frantic rate of star formation without blowing itself apart. It explains how a black hole could be force-fed gas faster than the Eddington limit would normally allow. The universe had built a superhighway system, and the traffic was moving at breakneck speed. This efficiency is frighteningly elegant. It suggests that the early universe was not a chaotic mess, but a machine tuned for maximum production. However, even with dark matter highways and cold gas fuel injection, there is still the problem of the engine itself. We know these galaxies are making stars, but when Webb analyzes the light from these stars, it finds something that shouldn't be there yet: pollution. When we look at the spectrum of a galaxy from 400 million years after the Big Bang, we expect to see a signature of pure hydrogen and helium. These are the only two elements created in significant amounts by the Big Bang itself. The first stars, the hypothetical population 3 stars, should be made of nothing else. They should be pristine. But Webb isn't finding pristine stars. It is finding stars laced with oxygen, carbon, and neon. In astronomy, we call anything heavier than helium a metal. To a stellar physicist, carbon is a metal, oxygen is a metal, nitrogen is a metal. These elements are the ashes of dead stars. You cannot make them in deep space. You have to forge them in a nuclear furnace, then blow the furnace up to scatter them. Finding metals in the very first galaxies, we can see, is like finding a Roman coin in a dinosaur fossil. It implies that a civilization or in this case, a generation of stars, has already lived and died before the scene we are looking at even started. This forces us to confront the mystery of the lost generation. We have never seen a population 3 star. They are the theoretical ghosts of cosmology. We know they must have existed because the universe started with no metals and now has plenty. Someone had to make the first batch. But they have eluded every telescope in history. The data from the universe breakers suggests a reason for this elusiveness. They lived fast and they died young. These first stars were likely monsters. Without heavy elements to cool the gas clouds they formed from the initial clumps of star stuff would have been enormous. A typical population 3 star might have been hundreds of times more massive than our Sun. Stars this big do not conserve energy. They burn it with reckless abandon. While our Sun will burn for 10 billion years, a population 3 giant might have burned through its entire fuel supply in just 2 million years. In cosmic terms, that isn't a life. It's an explosion. If the early universe was populated by these giants, it explains the chemical paradox. These stars would have ignited, shone with the brilliance of a million suns, and then detonated almost instantly. Their deaths would have been cataclysmic, seeding the surrounding gas with the first breath of oxygen and carbon. So, when Webb looks at a galaxy at redshift 12, it is looking at the survivors, the second generation, forming out of the wreckage of that first violent epoch. This creates a picture of the early universe that is far more dynamic than we imagined. It wasn't a slow awakening. It was a flashbulb popping, a sudden, synchronized burst of massive stars that lit up the dark, enriched the cosmos, and then vanished, leaving behind the seeds for the galaxies we see today. But there is a catch. If this lost generation was so violent, their explosions should have done more than just create chemicals. They should have blown the gas away. Supernovae are messy. They create winds that push gas out of a galaxy. If you have too many explosions, you stop star formation because you blow away all the fuel. This is called feedback, and it is the usual regulator of galaxy growth. It's the universe's way of saying slow down. Yet, the universe breakers didn't slow down. They kept growing. They held on to their gas. This implies that gravity in the early universe had a grip of iron. The dark matter halos were so deep, and the cold flows of gas so powerful, that even the explosive death of a million giant stars couldn't halt the process. The gravity trapped the debris, recycled it, and forced it back into the next generation of stars. It was a closed loop of destruction and creation, spinning faster and faster. There is a human reaction to this kind of data, a mix of exhilaration and disorientation. For years, astronomers have built models based on equilibrium, the idea that forces balance out. Gravity pulls in, pressure pushes out, heating balances cooling. The universe Webb is revealing is a universe out of balance. It is a universe dominated by runaway processes, runaway collapse, runaway accretion, runaway enrichment. It brings us back to the idea of the voice of the data. If the old data whispered, this new data is screaming. It tells us that we have underestimated the universe's capacity for change. We often think of the laws of physics as rigid bars in a cage, But extreme environments test the flexibility of those bars. In the high density, high energy environment of the cosmic dawn, the interplay between radiation and matter becomes incredibly complex. For instance, consider the fog. After the Big Bang, as the universe cooled, it became filled with neutral hydrogen gas. This gas was opaque to ultraviolet light. If you had been there, you wouldn't have been able to see the stars. The fog would have swallowed the light. To clear the fog, you need energy. You need intense ultraviolet radiation to strip the electrons off the hydrogen atoms, a process called reionization. We used to think this was a slow process, done by billions of faint, small galaxies over a billion years. But the universe breakers are bright enough to burn holes in the fog all by themselves. Webb is finding giant bubbles of transparent space around these early galaxies. They are like lighthouses in a storm, carving out cavities of clarity in the murky gloom. This suggests that the universe didn't clear up uniformly. It happened in patches, driven by these overachieving galaxies. This changes the narrative of our own origins. We are here because the fog cleared. We are here because the heavy elements were forged. We are here because the galaxies stabilized. And it turns out all of that happened because a few rare, massive, impossible objects did the heavy lifting when the universe was barely out of the cradle. They were the pioneers. They burned through the darkness so the rest of the cosmos could follow. But as we admire these giants, a subtle realization begins to dawn on the researchers analyzing the spectra. The numbers, while consistent, are dangerously close to the edge. To make a galaxy this big, this fast, with this much chemical richness, you need to push every single parameter in the standard model to its absolute limit. You need the dark matter to clump instantly. You need the gas to flow with zero resistance. You need stars to form with 100% efficiency. You need black holes to eat without choking. Nature rarely operates at 100% efficiency. Entropy usually takes a cut. Friction usually slows things down. When a model requires perfection to work, it is usually a sign that the model is missing something. It's like trying to explain a magic trick by saying the magician just moved really, really fast. It's technically possible, but it's more likely that there is a trapdoor you haven't seen. This is where the excitement lies. We are staring at the universe breakers and realizing that efficiency might not be the answer. The answer might be a new variable. Maybe the trapdoor is in the nature of dark matter itself. We assume it is cold and collisionless, that it doesn't interact with itself. But what if early dark matter was fuzzy? What if it had a slight interaction that could change how the halos formed? Or maybe the trapdoor is in gravity. We assume gravity is constant across all scales, but on these vast cosmic scales, in the density of the early universe, could there be a subtle deviation? The Webb telescope has done something more profound than just finding big galaxies. It has pushed the standard model of cosmology against the wall. It hasn't broken it yet, but it is making it sweat. We are looking for the new physics, the hidden layer of reality that dictates how the universe behaves when we aren't looking. The universe breakers are the fingerprints of that hidden layer. As we move from the structure of the web to the implications for our understanding of reality, we have to ask, if the universe can do this, what else is it hiding? if it can build a metropolis in the time it takes to be, what does that say about the dark future we predict for it? We have spent decades predicting the heat death of the universe, the slow, inevitable fade into nothingness. But a universe that starts with such explosive creativity, such defiance of the expected rules, might have a few more surprises left in its timeline. The story of the early universe is not just a prologue, it is a warning. It warns us not to underestimate the potential of matter and energy. It warns us that our timeline is provisional. And most of all, it invites us to rewrite the ending. Because if we were wrong about the beginning, if we missed the monsters in the dark, the invisible highways, and the impossible stars, then we have to wonder, what are we missing about the present? The data from Webb is not just a look back. It is a mirror reflecting our own ignorance. And in that reflection, we are finally beginning to see the true face of the cosmos. It is not a passive void. It is an active, aggressive, and creative force, and it is far from finished. It is tempting, when faced with data that defies expectation, to burn the whole house down, to look at the universe breakers and say that the Big Bang Theory is dead, or that our understanding of gravity is fundamentally broken. But science is rarely about burning houses. It is about renovation. As the initial shock of the Webb data wears off, a more nuanced reality is beginning to emerge. We are not necessarily looking at a broken universe. We are looking at a misunderstood one. We are realizing that our simulations, for all their complexity, were too conservative. They were too polite. The primary suspect in this case of mistaken identity is a phenomenon known as bursty star formation. In our old models, we assumed galaxies grew like trees, adding mass at a steady, predictable rate. A little bit of gas falls in, a few stars turn on, and the galaxy gets slightly brighter. It was a smooth, upward curve. But the universe Webb is revealing is not smooth. It is epileptic. Newer, high-resolution simulations suggest that early galaxies didn't grow steadily. They grew in violent, explosive spasms. Gas would crash into the core, triggering a frantic episode of starbirth that lit up the galaxy like a firework. Then, the energy from those stars would blow the remaining gas out, and the galaxy would go dark, dormant for millions of years until gravity pulled the gas back in for another round. If Webb catches a galaxy during one of these bursts, it looks incredibly bright. It looks massive. We might calculate that it has 1 billion stars because it shines with the light of 1 billion stars. But in reality, it might be a much smaller galaxy that is simply screaming its presence into the void during a brief window of peak activity. We may have mistaken brightness for mass. We saw the flash of a camera and assumed it was the steady beam of a lighthouse. This distinction matters. It means the laws of physics don't have to be rewritten. They just have to be applied dynamically. It means the universe breakers might not be monsters after all. They might be tricksters. They are small galaxies punching above their weight, masquerading as giants because they are running their engines in the red zone. This creates a selection bias. Webb is drawn to the brightest objects. We are seeing the outliers, the freaks, the overachievers. We aren't seeing the millions of normal, faint galaxies that are quietly obeying the laws of physics in the background. We are judging the entire population of the early universe by its loudest celebrities. And yet, even with this correction, the unease remains. Even if we account for the bursts The black holes are still too big. The chemistry is still too rich. The bursty theory explains the light, but it doesn't fully explain the maturity. This brings us to the final, and perhaps most important, realization of this entire journey. It is a realization about us. For centuries, human beings have tried to impose a narrative of gradualism on the cosmos. We like things to be slow. We like evolution to take millions of years. We like geology to take eons. We feel safe when the universe changes at a pace we can measure with a calendar. But the universe is under no obligation to be slow. The data from the dawn of time is telling us that nature is capable of fast-tracking complexity. Under the right conditions, extreme density, extreme heat, extreme gravity, matter can organize itself with a speed that looks miraculous to our slow-motion eyes. This has profound implications for life. If the universe can build galaxies and forge oxygen in the first few 100 million years, it means the ingredients for life were available almost immediately. We used to think the early universe was a sterile wasteland, and that life could only emerge billions of years later, after generations of stars had enriched the void. But if oxygen and carbon were present at redshift 12, then rocky planets could have formed at redshift 10. Water could have pooled on surfaces while the universe was still dense and warm. It opens the dizzying possibility that we are not the first, that life didn't have to wait for the Milky Way to settle down, that the potential for biology is baked into the physics of the Big Bang itself, ready to activate the moment the temperature drops enough to let chemistry happen. We are not the latecomers to a desolate party. We are simply the latest guests in a house that has been lived in for a very long time. This shifts our perspective from isolation to connection. The physical processes that created the universe breakers, the gravitational collapse, the nuclear fusion, the chemical enrichment, are the exact same processes that created the iron in your blood and the calcium in your bones. The story of those distant, impossible galaxies is intimately our story. They are the prologue that made the book possible. So, where does this leave us? We stand today with a map that is full of holes. The standard model of cosmology is frayed at the edges. We have found monsters where there should be emptiness. We have found maturity where there should be infancy. But this is not a crisis. This is the best possible news. If the map were perfect, if Webb had looked back and seen exactly what we predicted, faint, boring blobs of gas, it would have been a tragedy. It would have meant we had already figured it all out. It would have meant the universe was small enough to fit inside our current equations. Instead, the universe has proven to be wilder, stranger, and more efficient than we dared to imagine. It has shown us that even in the dark, even in the silence of the beginning, there was activity, there was structure, there was a rush toward existence. The universe breakers are not breaking the universe. They are breaking our arrogance. They are reminding us that we are observers, not authors. We don't get to decide how fast a galaxy forms. We don't get to decide how quickly a black hole eats. We only get to watch and learn and update our little books of theories. The James Webb Space Telescope has only scratched the surface. We have surveyed a tiny fraction of the sky. In the coming years, we will look deeper, we will find objects that confuse us even more. We will likely find things that contradict what I have told you today. And that is exactly how it should be. Science is not a monument to truth. It is a ladder. We climb it one rung at a time, and sometimes the rung breaks, we fall, we dust ourselves off, and we build a stronger rung. The too much light, too early problem is just the latest broken rung. We are fixing it. We are adding heavy seeds to our models. We are adding cold accretion flows. We are adding bursty star formation. We are building a more complex, more chaotic, and more beautiful model of reality. The universe that is emerging from this data is not a cold, mechanical clockwork. It is a dynamic, evolving ecosystem. It is a place where matter yearns to be complex, where gravity and gas dance a frantic tango to build the lights that banish the dark. We used to look at the night sky and feel small because of the distances. Now, we should look at it and feel awe at the speed at which chaos became order, the speed at which the nothing became the something. The story of the universe is not a story of a slow, inevitable grind. It is a story of a sprint, a race against expansion, a desperate, beautiful struggle to create stars before the dark energy pushes everything away. And looking at those ancient galaxies, those bright beacons from the dawn of time, one thing is undeniably clear. Gravity won, the light won, and because they did, we are here to wonder about it. The search continues, the mirrors are still watching, and the universe, as always, is waiting to surprise us. If you want to keep exploring the impossible with us, make sure you are subscribed. The universe is vast, and we have a lot of darkness left to map.